The concept of rate of change. Welcome to this lesson on the concept of rate of change. Let us begin with our first slide, which serves as an introduction to the topic. In the study of mathematics, and specifically within calculus, it is important to realize that the derivative is not merely a formula used for finding the slope of a line. Instead, it is a powerful tool that allows us to measure exactly how one quantity changes in response to another. This fundamental principle is what we call the rate of change. To understand this, we must first look at the relationship between variables. When we say that a quantity, y, varies with another quantity, x, we are implying that y is the dependent variable, meaning its value depends on what happens to x, while x is the independent variable. The rate at which y changes with respect to x is mathematically represented by the derivative, which we denote as di by dx. Throughout the rest of this presentation, we will build upon this foundation. We will move from this general definition to a more precise mathematical breakdown, explore how this applies to real-world scenarios like distance and time, and finally, solve a practical problem together to solidify your understanding. Understanding the mathematical definition. Now that we have introduced the general idea of the rate of change, let us dive deeper into the formal mathematical definition. If we have a quantity, y, that is defined as a function of x, which we write as y equals f of x, then the derivative dy by dx, which can also be denoted as f prime of x, represents the instantaneous rate of change of y with respect to x. To help you apply this in practice, let us break the concept down into a step-by-step process. First, we must consider dependency. Before performing any calculations, you must identify which variable depends on the other. For example, if we are looking at the area of a circle, the area changes based on the size of the radius. Therefore, the area is the dependent variable, and the radius is the independent variable. Second, we look at the derivative. The process of differentiation allows us to derive a new function. dy by dx, this new function is powerful because it provides us with the rate of change for any possible value of x. Third, it is crucial to understand the concept of the instantaneous rate. You may have previously learned how to calculate an average rate of change over a specific interval. However, the derivative is different. It gives us the instantaneous rate of change, meaning it tells us exactly how fast y is changing at one specific moment or point. Finally, we have specific point evaluation. To find the exact rate of change at a particular value, which we will call x0, we simply substitute x0 into our derivative function. Mathematically, we denote this as dy by dx evaluated at x equals x0, or more simply, f prime of x0. Once you are comfortable with this theoretical definition, we can move forward to see how this works in a real-world context, such as the relationship between distance and time. Real-world application, distance and time. Now that we have established the theoretical definition of the derivative, let us move on to a practical application to see how this works in the real world. One of the most common examples of the rate of change is the relationship between distance and time. In the study of physics, if we let the letters represent the distance covered by an object and the letter t represent the time taken, we can see that the distance depends on the time elapsed. Therefore, we say that is a function of t, which is written mathematically as equals f of t. Applying the concept of the derivative that we discussed in the previous slide, the rate of change of distance with respect to time is defined as velocity, represented by the letter v. In mathematical terms, this is expressed as v equals ds by dt. To understand what this means in a physical sense, if the derivative s by dt is constant, it implies that the object is moving at a steady speed. On the other hand, if s by dt is changing, it tells us that the object is either accelerating or decelerating. Now that we understand the relationship between distance, time, and velocity, let us proceed to the next slide, where we will apply these principles to a worked example. Worked example. Now that we have established the theoretical foundation and the relationship between distance and velocity, let's apply these concepts to a practical worked example. Please look at the scenario provided. We are tracking a particle moving along a straight line. Its distance, represented by the variable s in meters, is defined by the function s equals 3t squared plus 4t plus 5, where t represents the time in seconds. Our objective is to find the rate of change of this distance, which, as we discussed in the previous slide, is the velocity, at the exact instant when t equals 2 seconds. Let us walk through the solution step by step. Step 1 is to clearly identify the given function. Here, our distance function is s equals 3t squared plus 4t plus 5. Step 2 is to find the derivative of this function with respect to time t. To do this, we apply the power rule of differentiation, which tells us that the derivative of x to the power of n is n times x to the power of n minus 1. Applying this rule to our specific function, the derivative of s with respect to t is the derivative of the quantity 3t squared plus 4t plus 5. This breaks down to 3 times 2t to the power of 1 plus 4 times 1t to the power of 0 plus 0, since the derivative of a constant is always 0. When we simplify this, we find that ds over dt equals 6t plus 4. Step 3 is to find the instantaneous rate of change. As we learned in our second slide, the derivative provides a general formula, but to find the rate at a specific moment, we must substitute the given value of t. Since we are looking for the velocity at t equals 2, we evaluate the derivative of s with respect to t at t equals 2. This gives us 6 times 2 plus 4. Calculating this, we get 12 plus 4, which equals 16. Consequently, our final result is that the rate of change of distance at 2 seconds is 16 meters per second. Pay close attention to these steps. As in the next slide, we will discuss some common mistakes to avoid so that you can ensure your calculations are always accurate. Common mistakes to avoid. Now that we have walked through a practical example of calculating velocity, let us discuss some common pitfalls. It is very important to be aware of these mistakes to ensure your calculations are accurate. First, let's talk about confusing the average rate of change with the instantaneous rate of change. Many students instinctively reach for the slope formula, y2 minus y1 divided by x2 minus x1. While this is a useful formula, remember that it only provides the average rate of change over a specific interval. As we saw in our previous example, when we want to find the rate of change at one specific point in time, we cannot use that formula. Instead, we must use the derivative. Next, be careful with variable identification. As we discussed in the introductory slides, you must clearly distinguish between the dependent and independent variables. Always ensure you are differentiating with respect to the correct independent variable. For instance, if a problem asks for the rate of change of area, a with respect to the radius, r, your derivative must be written as dA by dr. Writing it as dr by d would be mathematically incorrect, as it would imply you are measuring how the radius changes relative to the area. Finally, do not forget the constant rule. You might recall from our worked example that the constant number 5 disappeared during differentiation. This is because the derivative of any constant value, a number without a variable attached to it, is always 0. Keep these 3 points in mind as we move toward our final summary of the topic. Key takeaways. To wrap up our lesson, let's go over the key takeaways to ensure you have a solid grasp of the concept of rate of change. First, always remember that the derivative, denoted as di by dx, represents the instantaneous rate of change of y with respect to x, unlike the average rate of change we cautioned against in the previous slide. This gives us the exact rate at a single moment. Secondly, regarding the notation, when you see di by dx with a vertical bar indicating x equals x naught, this is simply the mathematical way of saying we are evaluating the rate of change at a specific point, x naught. In practical terms, As we saw in our distance and time example, the rate of change of distance with respect to time is defined as velocity, which we write as v equals ds by dt. Finally, to successfully solve any rate of change problem, just follow the three-step process we used in our worked example. First, identify the function. Second, differentiate that function to find the derivative. And third, substitute the given value into your derivative to find the final result.